In this example, we'll be once again visiting volumes by revolution. Determine the volume of the solid obtained by rotating the region bounded by y equals the cube root of x, y equals x over 4, in the first quadrant, specifically about the y-axis. So the first step here is, again, to draw the region that we're playing with. And the idea is that if I'm looking at the cube root of x, that's going to look something like this. Next thing I'm going to look at is y equals x over 4, which is nothing more than, I'm going to go ahead and write these things down. y1 is equal to the cube root of x. y2 is equal to simply 1/4 x. It's the same thing as x over 4, but I'm going to write it this way so I can identify that it's nothing more than a linear function. Knowing that it's a linear function, and again, if you need to, you can go ahead and view this object in a graphing calculator. It'll look something like that. And then it also restricts us to say that we're only in the first quadrant. So that means we're only working right here. So that tells me that I need to be bounded by the x-axis, the y-axis, in terms of the positive axes setups. So with that drawn, the idea is now I've got to figure out where this equation, okay, and how am I going to cut this? Well, because I'm taking this object and I'm rotating around the y-axis this time, not the x-axis, I'm going to redraw this image. It's going to look something like this. I'm going to exaggerate it a little bit so it's easier for me to work with. So you'll notice, again, that image looks something similar to that, where this bottom line should be a straight line and this top line should be a curved line. You'll notice that this is y1 and this down here is y2. We're going to go ahead and reflect it over the y-axis this time because that's what we're rotating it around, which means I'm going to draw the exact same object to the best of my ability over on this side. So this one's going to get a little bit more complicated. You'll notice now that I'm going to go ahead and draw the circular cross sections this way because that's the way it's being rotated. So now what it looks like is we've got this cone. However, inside the cone, we've got this curved, drilled out section. Okay, so again, we've got this cone, and we've got this curved, drilled out section. So the middle section is somewhat empty. If I were to try and draw the cross sections of this, I would see that I have what we call an annulus. An annulus is simply a circle with another circle inside of it. So this section in the middle is cut out. So the area I'm actually trying to find is the area of this outside what looks like a donut. Okay? For us to do that, the idea is that for each one of these cross sections, we're going to find a capital R value. That capital R value is simply going to allow us to determine what the area of the large circle is. Okay, so I'm going to go ahead and do the area of the large circle. And then the small area here, I'm going to use lowercase r for that. I'm going to go ahead and find the area of the small circle. And that's simply going to be another pi, but lowercase r squared. So knowing that these two are my r squared values, the values that I'm actually going to go ahead and find the area of each cross section utilizing, I've simply got to figure out what capital R and lowercase r really are in this object. And you'll notice right here that this small circle is probably the clearest I'm going to be able to get. And that small circle, its r is this value right here. You'll notice that that value right there is a cut that is horizontal. So again, all of these circular cross sections are drawn in a horizontal pattern. If you recall from the previous examples, the horizontal pattern should be in terms of a dy. Okay? So that means my bound should be y equals something to something. Based on that information, I should be able to determine what this value is and what this value is, based on knowing that this is supposed to be in terms of y. Well, this location right down here where they intersect, that's obviously 0. The upper section right here is a little bit more complicated, but it's going to require that we set these two things equal to each other. So before I get to that, again, one more time, the idea is draw the region, visualize the way that it's being rotated in order to visualize how you need to cut this to get a disc, and this right here is actually what we call the washer. So for a washer, the rules don't change. What changes is simply the formula. You're going to simply have the larger area minus the smaller area inside of that interval. Okay, in terms of either dx or dy. In this case it's dy, but it could be in terms of dx. There's nothing telling us other than the image which way we have to cut this. Again, we have to cut this one in terms of dy because that's what will allow us to get the cross sections to be discs or washers. So I'm now going to go ahead and start working at evaluating all the pieces of this interval. I need to figure out what capital R is. I need to figure out what lowercase r is. I need to figure out my bounds a and b. My a bound I already have. Again, that's the lowest value on this region. I'm going to cut this thing vertically up until this point right here. This point, if it helps, is this space right here. It's that thing right there. So I've got to figure out these two functions intersecting. Now, in most cases, what we would do is, because of the way that these are set up, I'd set the cube root of x equal to 1/4 of x, and I'd attempt to solve this. But knowing for my sake that I'm supposed to get y equals tells me that maybe I shouldn't work with these x equals functions. So right here, I'm going to change y1 to be x equals y cubed. I'm now going to call that f1. I'm going to call it f1 to identify that this is the first function that we're looking at. That is f1. So it either is going to be this equation here or this equation here. Secondly, I'm going to go ahead and relabel this one as f2. Okay, in terms of f2, I'm going to solve this equation for x equals as well. X equals, I'm going to multiply both sides by 4 and get 4y. Now, with that being done, again, you could attempt to solve this equation, but I'll be honest with you, I think that's going to actually be more complicated than you want. But if I look here at these two equations, I can do the same thing I did. Instead of setting y1 equal to y2, I'm going to set x1 equal to x2. So I end up with y cubed equals to 4y, which if I go ahead and solve this like I would any other polynomial, I'll subtract the 4y over. I'll factor out a y, giving me y squared minus 4 equals to 0. This one tells me y equals to 0, which I already had. And this gives me y equals positive 2 or negative 2. Knowing that I'm working in the first quadrant, that tells me that my y value right here is y equals positive 2. So that means that my upper bound is going to be 2. So again, from here, that's y equals 0, to here, that's y equals 2. So now I know what my y values are going to be picked as. My next step is to figure out what is my radius values in this, again, washer. My capital R is going to be, if it helps, from the center of this graph out to the furthest point. But you'll notice, what is the furthest point? Well, the furthest point is this line every single time. Again, we want to know what the area is of the whole circle, and then we'll subtract from that the area of these tiny circles. So the area of the entire circle in every single one of these cross sections, the large circle, is going to be the radius going out to this line. The radius out to that line is that line, which means that the radius out to that line is going to be a distance from here to here, which is a distance of x. X equals that line. X equals 4y. Again, one more time, very, very carefully. We're going to go ahead and see that y2 equals 1/4 over x. That's the equation of that line. We're going to identify that x equals 4y is the same equation of that line. We're going to say that the distance from the center out to that line is a distance of x, and that x is going to be 4y. Why are we going to use that? Because we need this equation to be in terms of dy. So my r is going to change. Every single little cross section in here is going to change. My capital R is going to denote by an x value, the x value such that we end up with 4y. So in this formula over here, I'm going to have pi. My r value is 4y squared. I'm going to subtract from that pi lowercase r squared. In this case, for me to find my lowercase r, again, I'm starting in the center here, and if this is starting to get a little bit messy, again, redraw the image to see it again. This is the center line. So from here to that function is my lowercase r. And again, you'll see those circles start to develop. That lowercase r is simply this equation right here. But keep in mind, that is going to be x equals, and that's going to be r, and that x correlates to the cube root function, which for x equals is simply y cubed. So this formula ends up being pi y cubed quantity squared. So this is, again, the conceptual understanding of this problem. This is the setup. After we've set it up, we're going to just treat it like any other integral problem. Step 1, how would I integrate something like this? Well, there's a couple of different things I could do. The first thing I'm going to go ahead and do is deal with those squareds. I'm going to have pi, 4 squared is times 16, y squared, minus pi, and then y cubed to the power of 2 is y to the power of 6 dy. If it helps, again, that pi gets in the way, you can go ahead and factor that pi out. So I have 0 to 2 multiplied by pi of 16y squared minus y to the 6th dy. And again, I should be able to identify that you can integrate it from here, increasing the power of this by 1, dividing by the power, doing the same here, and then plugging in the bound of 2 and plugging in the bound of 0.